Okay. So hi everyone. Welcome to the eighth meeting of our reading group about data attribution. So today, Ting and I will talk about the data attribution for copyright issues. So we will introduce four papers that are related to the copyright issue for generative AI and training data attribution. So first, we will give an introduction about the copyright issue in the generative AI and some potential solutions that are inspired by the TDA methods. And then we will introduce two papers towards building a royalty model for the generative AI. And after that, we will look into the efficient method that calculates the Shapley value within one training process and its application to the copyright issue. So in the end, we will discuss an interesting relationship between the similarity and the copyright infringement. So, and as well as its effect on the current copyright solutions. So first, what's copyright? So copyright belongs to a type of intellectual property or IP, as we know. So some other intellectual properties include the patent and the trademark. So copyright is defined as protecting the original works of authorship as soon as the author fixed the work in a tangible form of expression. So this expression includes music, images, articles, and so on. So it means that the copyright is actually close to us, maybe more than you think. Every time you post something on the internet, you could be a copyright holder. And the image you see, the movie, the movie you enjoy, and the article you read are almost all copyrighted. So as you probably know, there are a lot of ongoing lawsuits against the generative AI companies. So including the famous New York Times cases, there are quite a few major news groups suing against the Microsoft and the OpenAI. And of course, similar things are happening to other companies that run in the generative AI in other domains, such as the Stability AI and Midjourney. So it's important because it could have a huge impact on the development of generative AI. So for example, in this news article, it was reported that the OpenAI claims that it will be impossible to train today's leading AI models without using the copyrighted materials. More pessimistic views even say that the copyright lawsuits could kill the companies like the OpenAI. So technical community has been searching for the solutions to this problem. For example, data filtering that filters the copyright content, or machine learning that tries to edit the models in a post hoc way. So what's in common about this for most existing efforts is that they all try to prevent the existing model from spitting out some copyrighted training content. So however, these methods are usually sophisticated and costly, and more importantly, they usually hurt the model's performance. In our work, we will try to approach the copyright problem from a different perspective. We will see two of them, like the privacy. Many copyright owners may be okay with their work being used if they are properly compensated. So an economic solution may be an earlier path, may become an early path to address this problem. To elaborate on this point, a proper economic solution could work well as how copyright works in things like online music or video platforms. So in addition, such an economic solution may even be necessary, at least for the near future. The AI capabilities are built on their training data. And in some cases, such as the artistic work, the data are concentrated of human labors. On the other hand, massive deployment of AI will dilute the value of human labor. So this brings social and economic problems that go beyond the copyright alone. So we have already seen that the strikes in the Hollywood last year against the wide use of the AI in the Hollywood studios. A proper economic solution may be necessary to mitigate the conflicts between the AI and the conventional human labors in the short term. So given this background, we will ask, how do we build such an economic solution? So in the first paper we will share, we focus on the music domain. Before we actually look into the generative AI, we will show you a case study about how things work in online media platforms like the Spotify and YouTube. Then we will see what the unique challenges when we move to the generative AI services. The fees paid to the music copyright owners are typically called royalties. So we will be looking at the royalty models for these platforms. So Spotify is actually a very simple model. Its revenue mainly comes from the users' subscriptions or advertisements. This forms a revenue pool, and part of it will be shared to the music copyright owners. So in practice, it usually first goes to some record labels or large copyright holders, and then it goes to the artists. So now what's important is that how is this revenue distributed among different copyright owners? On Spotify, the shares among them are determined by the so-called pro rata method. So which basically means that we weight the shares by the number of times each music is consumed by the users. And on YouTube, we also first have a revenue pool and share it with the copyright owners. The tricky thing here is that, that the YouTube video may or may not contain some copyrighted music. And it may also contain multiple copyrighted music. And these videos are made by the YouTubers who don't always clearly annotate it. So when we want to calculate the pro rata shares for copyright owners, we only know that the views of the YouTube videos, but cannot directly attribute that to the copyrighted content containing these videos. YouTube developed this content ID system that can detect the copyrighted content used in each video. Then we can attribute each video back to the copyrighted content used in it, and when calculating the revenue shares. So now when it comes to the AI music platforms, we can imagine a similar revenue sharing mechanism with the videos replaced by the AI-generated music. So, however, here's a new technical challenge. That is, how do we attribute the generated music back to the copyrighted training music to calculate their revenue shares? So in this reading group, the answer is quite straightforward. We address this challenge by applying the data attribution methods. So here is a high-level idea. Suppose we remove a training data point or a subset of the training data points from the training dataset, and then we will train the model on the remaining data. So now for the piece of the music generated by the original model, we measure the change of likelihood of this piece on the new retrained model. If the likelihood drops a lot, then it suggests that the removed training data are very influential to the generated music. So this data attribution score can be used to determine the pro rata share of copyright owners in the context of music generative AI platforms. The computational copyright paper did some experiment on the symbolic music generation and the LDS of the off-the-shelf methods, shown that the current method could efficiently achieve reasonable approximation accuracy. And similarly, data attribution methods can also be used to determine the share of copyright owners in the context of the music AI generation platform. The problem definition in the image AI generation platform are pretty similar to the one designed for the AI music platform. So then we will invite Ting to introduce the next two papers.
Yeah, thanks, Junwei. And yeah, let me share my screen. Can you see my screen now?
Yeah.
Okay. Yeah, so thanks, Junwei, for presenting the first paper. And along with the previous definitions and background, we're going to introduce the second paper, which is titled as an economic solution to copyright challenges of generative AI. So this figure actually shows the main framework introduced in the paper, where the training dataset consists of various copyrighted paintings from different copyright owners. These data is used to train a generative model that can generate new images based on people's prompts. And for a specific AI-generated image, we would like to access the contribution of each copyright owner based on the Shapley value, which determines what is the portion of compensation each person will get. So this is a fairly general framework that we can actually plug in any kind of data attribution method. Just as mentioned by Junwei, we can also plug in attribution method like track or tracing to replace this Shapley value in this figure. So to be diving deeper into the figure shown in the previous slide, the author basically proposed a two-step approach. So for step one, we will evaluate the value of data through data Shapley. So the detailed procedure is that we will first train various models, each trained on a specific subset of the entire trained data set. Then we will compute each data's subset utility based on its ability to generate content similar to the model, or the full model. And the definition of the full model is actually the model trained on the full data set. And finally, these utility values can be used to compute the value of each training data point. And for step two, given these value of training data point, we can simply allocate compensation shares among copyright owners for a specific AI-generated content based on the value of each data point in the trained data set. So the intuition is that a larger share will be assigned to copyright owners whose data significantly contributes to the model's performance in generating content similar to the model that trained by the full data set. So here we will introduce a bit on the exact definition of the utility function that we mentioned in the previous slide. So just to give some notations here, we will call the full data set D, and S can be any arbitrary subset of D. So now our goal is to access the goodness of the model that trained on subset S instead of full data set D, which is the main component to compute data Shapley values. So a fairly intuitive way to think of this is to consider the likelihood of generating XGen. And here XGen is just some content or some data point that generated by model, which is trained on full data set D. So the exact formula can be written as the figure on the left, which is the log likelihood of generating XGen by the model trained only on the data subset S. This is basically the definition of the utility function of subset S with respect to XGen. And this is basically formulated as the V function in the figure on the left. However, in real-world scenarios, generation might also include some prompt interactions from users. So we can model all these interactions or actions as in event queue, and the formula can be modified as the figures on the right, where it includes an offset term on the denominator that computes the log likelihood when no training on copyrighted items. So you can see there's a empty set replacing the subset S. So this can be seen as a baseline model and to correct the term on the left. And note that both numerator and denominator are conditioned on this specific event queue. So after the definition of the utility function mentioned in the previous slide, it is now really straightforward to compute the data Shapley value, which is phi I, where I is each trend that corresponds to each trend data point I. So in brief, we will just compute the marginal contribution of data point I. So basically, this V function of S union I minus V function of S. This will measure the marginal contribution of data point I. And we will just compute a weighted sum over various terms of this V function, and we can obtain our phi I for each data point I. So at the bottom figure, we can just compensate each copyright owners based on the phi I values that we just computed, and to compute the different royalty share to the copyright owners based on the data Shapley value calculated. In addition to the framework itself, the author also mentioned some practical improvement to avoid huge computational overhead when computing the Shapley value. And the first one is simply a Monte Carlo method to approximate the exact data Shapley value. We know that for exact data Shapley value, we have to train like exponentially many models with respect to the number of trained data. And the other one is to avoid training from scratch to gather models trained on different subset S. So here I provide a very simple example. So if we are trying to evaluate a model that is trained on subset S equals to data point number 1, 3, and 5, then actually this model can be approximated by model that trained on a smaller subset, which is S-clone equals to 1 and 3, and we can just fine tune it on data point 5. So this is just a very simple idea, but we can actually avoid training from scratch and replace it by fine tuning models trained on smaller data sets. So this can somehow save a lot of time when computing the exact data Shapley value formula. And in this paper, the author also conducts some experiments for various applications, and we'll briefly go through all this. So the first one is basically identifying relevant copyright owners. So I think this should be the main applications that we're looking for. So we can observe that the proposed method is quite effective to attribute these AI-generated images back to the correct copyright owner. So you can see the diagonal here is having the darker color because the SRS, which is the royalty share score, is larger. And also, there is another application, which is to accessibility of the proposed framework in distinguishing images that might be attributed back to multiple copyright owners. So you can see that this experiment shows that this SRS can also identify Van Gogh and Monet as the top two influencers or having the top two most shares. And also for non-copyrighted data, the intuition is that if we generate some images that didn't have any, didn't relate to each of the copyright owners, then we can expect that the SRS should be uniform. So this also satisfies our expectation. And the final thing is that not only the absolute value of the SRS is important, but also the relative ranking is also quite important to distinguish different level of similarity to the images that we want to do attribution. So this experiment also accurately reflects the expected ordering. So they somehow demonstrate the robustness in discerning the relative significance of contributions from diverse data sources. So that is the end of the second paper. And now we will switch from framework style of papers for royalty share to another like more general data attribution method. So this will be like a very recent developed method. And also because this paper has a specific paragraph discussing the application to solve copyright issues for generative AI. So we include this paper as well. So this paper is called Data Shapley in One Training Run, which redefines the traditional definition of data Shapley and solves some downsides of retraining-based data Shapley. And we will also provide some details of the method to some extent and discuss a little bit on the experiments about copyright issues. So first of all, let us discuss some existing data Shapley method. So with the price of high computational cost, the advantage of retraining-based data Shapley is actually its good property. So let us say it satisfies the 4 axioms, which is these listed here. I'm not going into details because these are quite common among data Shapley method literatures. But intuitively, these are the properties that when we wish a good data attribution method should have. However, there are like 3 main limitations of retraining-based data Shapley method, which are computational burden, inability to value data contribution to a specific trained model, and unstable valuation results for stochastic training algorithms. We'll also detail a little bit here. So first of all, very obvious that the computation burden comes from the extensive retraining when calculating the Shapley value. So the definition is down there in the figure. So again, we can see that we have to calculate a lot of marginal contribution of data point Z in interest, and we have to train a lot of model on different subsets as of the full trained data set D. So we have to train like exponentially many models with respect to number of trained data points. This is basically the most time-consuming part to compute exact data Shapley. And secondly, another issue is that while we're only interested in the model trained with the full data set, because that is the model that we have in hand, you can observe that the formula of Shapley value, which is definition down there, actually access like various models trained on different subset S, which are just subset of D. This indeed is the definition of Shapley value, but it will incur some discrepancy between what we calculate and what we are really interested in. So there should be some difference there. And this will cause the inability to access a specific trained model that trained on full data set. And finally, since the utility function U here often includes a stochastic learning algorithm, the randomness coming from random initialization or random batch selection will cause instability when computing utility function and a substantial noise for Shapley value computation. So these are the main 3 limitations, and this paper aims to solve those simultaneously. And before diving into this paper's method, we'll give some general notation constructing normal or conventional data Shapley. So again, we might want to define the utility function here that we can use to compute Shapley value, but now we're like in a more general scenario. So basically here on the figure on the top is the utility function U. It's a function that takes a dataset as input and output a real value. And this real value or a scalar is basically the value of the dataset. So to be more specific, we're asking a question that can we use this training set as to train a good model trained by a learning algorithm A? And if we can, how good is it? So this specific utility function is trying to tell us how good this train model is. So to be more specific, we will first train a model on dataset S, and by learning algorithm A. So this algorithm can be like SGD or anything else, and it will involve a lot of different random selection, random batch selection, random initialization, so on and so forth. And after training, the output of A will be a model, which is like normally the final checkpoint of the model. And we can use this perf, which is just a short writing of performance. We will evaluate this model checkpoint, final model checkpoints on some holdout validation data set to compute the performance metric. So for example, it can be just accuracy on the validation data set for a classification model, for a classification task. So after the definition of utility function, we can just plug it in to the formula down below. And this is basically the formula of data Shapley again. So given any utility function U and a trained data point Z in interest, which is probably Z, some Z in the full data set D. And we can calculate this data Shapley value based on the formula in the figure down below. So before we're really heading into the details of inrun data Shapley, which is the name of the method the author proposed in this paper, I would like to share some intuitions and insights about how inrun data Shapley solves the three aforementioned downsides of retraining-based data Shapley. So just to recap, the name of the paper is called Data Shapley in one training run. So the first downside of the retraining-based data Shapley is the computation burden. And just a spoiler alert here is that we are not going to train a lot of models on a lot of different data subsets. We will only train one model through one training run, just as the title said. So this method somehow will not cause this kind of computational burden. And the second is about the ability to access the performance of a single model in interest. And it is also naturally solved because we only focus on a single training run of a single model. So we will just only train one model. We are not estimating the data influence or data attribution through a lot of model trained on different subsets. We are only training one model using full data set. So there's no issue about accessing the model performance in interest. And the final one is about the randomness incurred through the training process. So basically about the stochastic learning algorithm. So why inrun data Shapley can solve this is because the inrun data Shapley will look into each iteration in the single training run and consider the random batch explicitly in each iteration. So these random batch are like specific realizations of the randomness included in the stochastic learning algorithm A. So we're now like computing the entire training performance on this specific train data and the learning algorithm A. So the randomness will be mitigated. So what is the main idea of inrun data Shapley? It's basically a divide and conquer style of method to compute data Shapley. So recall that the upper right corner here, which is the utility function definition, this is the conventional definition, which actually involves a bunch of training iteration secretly inside the algorithm A. So we know that this A is basically a stochastic learning algorithm. It might include like 20 epochs, 30 epochs, or 40 epochs, and it will finally reach the final model checkpoint. And we will evaluate that single final checkpoint by this performance metric So this A actually includes a lot of training process. There's a lot of things going on in this A, but we can where we don't have any control over. So we can call it something like a global utility function. So this conventional definition is more like a global utility function. And this paper is basically trying to decompose the utility function from global to a more local aspect. So the authors proposed to look at a more detailed and local utility function that is manageable and which can give like step-by-step assessments that capture the effects of training data points on the weight updates and provide a more fine-grained perspective of how individual training data points contribute to the model's performance at each step. So the main difference is that we are switching from measuring impact of dataset S across the complete training process to a scenario that we're measuring impact of subset S in each single iteration. So to be a little bit more specific, if we have capital T training iterations through this single training run, then our original utility function, which is the figure up there, we only define one utility function for the entire train process, which is just the performance of the trained model after capital T train iterations. And now the author proposed a new utility function. And note that this new utility function will specific for each iteration, T, small t here. So let's say the capital T equals to 10, then the original utility function doesn't really care about this 10, but it will only have one utility function across the entire training process. But for now, the new one defined by the author of this paper, we will actually have 10 different utility functions defined for each iteration. And it is basically the loss change between iteration T and T plus 1, evaluated on data point Z val. So basically the figure in the bottom, this UT. So we switch from U to UT, then this UT is specific for iteration small t. And it is defined by the loss of the model evaluated on Z-val, but with the parameter T plus 1, and minus the loss evaluated on Z-val, but on the parameter at iteration T. And here, this WT plus 1 is just the updated parameter in iteration T plus 1, which is just the parameter WT minus the learning rate eta T times the summation over the gradient. So here, note that this paper somehow makes the assumption that we are using iterative learning algorithm and more like in a SGD form. So based on this newly defined local utility function, now we can construct our in-run data sharply. So firstly, we just newly defined the utility function for a single gradient update, which is just the figure on top of this slide. And what we can do is just define the S to be the subset of BT. So what is BT? BT is the real batch selected for iteration T. So it is the realization of the randomness included in learning algorithm A, and we will really draw this random batch and make it BT. And now we will switch our focus from the entire full data set to BT. And this S in the definition of local utility function will be defined as subset of BT. And after we define the utility function of a single gradient update, or you can call it like an iteration, we can actually follow the exact same definition to compute the data Shapley value. So just what we saw like various times, like the marginal contributions and over a lot of different models trained on different subsets, and we can compute that data Shapley value based on that formula, considering all possible subset S of the real batch BT for iteration T. But know that we have a caution here. So there's still some problem here that we will discuss a little bit later in this slide. But hold on for a second. So we have this data Shapley for a single gradient update. Then we can compute data Shapley for the entire training process. So actually, what we want to do is just to redefine a new global utility function U, which is shown on the left. On the right here, US will be defined as the summation over UT. So it's just a summation over T different utility function, local utility function. And we can also define this phi z u as well by summing over phi z ut. And you might wonder, what is phi z ut? It is just the data Shapley for one specific iteration. So what is this caution is that this phi z ut still have some problem. The problem here is that even though we have shrink our definition of utility function, we didn't really solve the problem since there are still a number of data points in each batch BT. So let's say we have 64 or 128 or 256 data points in a batch. We still need to consider 2 to the power of 64, 2 to the power of 128, or 2 to the power of 256 to compute data Shapley for this single iteration. Although it's like significantly fewer than 2 to the power of training data, number of training data, but it's still a lot of models that we have to train and we have to evaluate. So we will need some other approximation techniques to overcome this specific computational burden. So now we define our in-run data Shapley. So to solve the problem that I just mentioned, we have to do some approximation for efficient computation. So now the remaining problem is actually to efficiently compute the phi z ut in the previous slide, which is the data Shapley value for the Tth iteration. So in order to obtain like a more tractable structure for this newly defined local utility function ut, the authors propose to compute the first and second order approximation of the local utility function for more efficient computation. So by utilizing Taylor approximation, we can first derive the first order in-run data Shapley, which is only considering the first thing here, which is the UT1S, and also the second order in-run data Shapley, which incorporate both terms, which is UT1S and UT2S on the up figure. And we will just ignore higher order terms. And note that since the local utility function is just loss change between two iterations, right? Just as we defined in previous slides, we can see that there is a weight parameter difference terms there in the formula. And due to the assumption that we made, we are using like Valina as GD. So we have this weight parameter updating form, which is this WT plus 1, the relationship between WT plus 1 and WT, which is the relationship between parameter between iteration T and T plus 1. And their difference is basically some learning rate times summation over gradient. And this utility function will now be a summation format because we now have this summation over gradients terms, and it will be easy to compute the marginal contribution within the data Shapley formula. So the data Shapley formula can be computed analytically, and we didn't really need to compute those like exponentially many models. And recall that we don't have the this kind of good property when we are considering global utility function when we're in a more traditional setting. And the right bottom figure here is basically the first order inround data sharply, which coincides with tracing model, a tracing method, tracing ideal method, which is also another famous data attribution method. And here I provide somehow a small remark here that the most used method, which is called tracing CP, is basically this kind of gradient dot formulation times the learning rate and do a summation. But we are only using some, like a handful numbers of checkpoints. So this tracing CP is something like approximation of tracing ideal, which in the sense that we have to compute this summation format in each iteration, for each iteration. And this tracing ideal is somehow equivalent to the first order approximation of the in-round data sharply. And the first order in-round data sharply just like another approximation of exact in-round data sharply. So it has this kind of chain kind style that somehow relates and connects this in-round data sharply to other famous gradient-based data attribution method. And finally, another efficient computation issue is that after we do this first order, second order approximation, we will end up a lot of gradient dot product and gradient product. How can we efficiently compute these kind of things? And this is also another very important problem. And the authors propose this ghost clipping technique, which actually enables computing all of the per sample gradients within one or two propagation without explicitly forming gradient vectors. So just a very simple example here. Let's say we're trying to compute the partial L, which is a loss function, partial L, partial W. This W is the one linear layer, let's say. And it will equals to this partial L, partial S times this partial S, partial W, where S is some output of the linear layer. And the second term can actually be considered as a constant. So can be formulated as this A. So it's basically, it can be formulated into partial L, partial S times this A. So the thing is that when we're trying to consider the gradient dot, which is this partial L1, partial W times partial L2, partial W, which is a gradient dot, we don't really need to form partial L, partial W at all by multiplying A and partial L, partial S. We only need to have two A's in hand and do a dot product, and also have two partial L, partial S in hand and do dot product and multiply them afterward. So we didn't really need to form the full gradient. So this is for first order approximation, and the author also proposed similar ideas for the second order differentiation, which is like more difficult and complex, but we refer the interested readers to check the original paper for more detailed proofs. They also come up with similar form of or application of this ghost clipping technique to compute the gradient hash and gradient product. So this is also a quick comparison between in-run data sharply and retraining based data sharply. So on the left, it is basically what we have talked about really much, training a lot of models on different subsets of data. And the utility function is measured on each model trained on each different subset. And we can compute the final data sharply value based on these utility function. And for the right figure, which is the in-run data sharply, we don't really need to train like that much models, and we just compute the utility function through the training process and like across each gradient update, which is like really computationally efficient. And now for experiment part, one specific important thing is runtime. So is in-run data sharply really fast, and how fast it is. So for the pre-training stage of GPT-2 small model, we can see that for the yellow curve, it is the regular training time. And you can see that for the in-run data Shapley, first order and second order using the ghost clipping technique, which is the second efficient computation method I just mentioned, it can just it would just incur like significantly fewer training time compared to direct computation. And finally, this is the experiment in this paper that relates to the copyright issues. So the question they're asking is that, do we really need to find exact match to identify relevant corpora in the training set? Or in other words, does contribution require memorization? And well, the experiment setting is that we'll use GPT-4 to paraphrase some of the selected corpus and compute the in-run data Shapley value and also like influence function scores. So you can also ask another equivalent question is that will this paraphrase paragraph recognize their original version in the trained data set? So again, spoiler alert here, the result is that even for heavily rewritten text, data attribution methods such as in-run data Shapley influence function here can still highly rank the original corpus as the top influencer in the trained data. And the implication is that trained data significantly influence AI output, AI generated output, even when the content doesn't like really resemble the original material, like token wisely. And here is the a figure, actually a table summarizing what I just said. So let's say we have a original wiki corpus as a one trained data point, and we construct synthetic corpus resemble this wiki corpus to different extent, ranging from partial exactly the same, paraphrase, significantly paraphrase, and similar topic. So the top one is the most resembling token-wise, and similar top one has the less similarity level. We can see that actually both for in-run data Shapley and influence function, partially exactly the same and paraphrase, they're always like ranked the highest. So if you just replace some random words in the original wiki corpus, or you just do a slight paraphrase, we can still, the synthetic corpus can still somehow recognize it being recognized. But even for the interesting thing is that even for a significant paraphrase, so you can see the third row here, the rank dropped from 1 to 30 something, but you can look for the last row, which is that if you compare this significantly paraphrased corpus to similar topic of the original corpus, it's still like it still stands out. So for the similar topic, all the different data attribution methods like first order, second order data Shapley or IF, there was rank low similar topic corpus as like 100 something or 200 something. So the significantly paraphrased version can still stand out. The contribution of this data can still be really, really high. And where the copyright owners of these trained data still need to be compensated to some level. And this is basically the end of the third paper. Thank you. So I will pass back to Junwei.
Yeah, thank you, Ting. Let me share my screen. You see it?
Yep.
Okay. So yeah, so finally we will visit our last paper, which points out an interesting point in the copyright law that could be inspiring to the future works. That is, the copyright law does not really protect all the aspects or all the elements in a work to the same extent. The original parts that is the parts that are different from the common works or generic works, are protected more by the copyright law. As you can imagine, if I learn a feature from the common knowledge, such as the sky is painted as blue, it cannot be classified as a copyright infringement to any specific work. So the image on the left is a very famous copyright infringement lawsuit. The left one is a photograph of President Obama, and the right one is a paint based on the photograph by another painter. So it's kind of very hard to say, or very objective to say, if the similar features in these two photos, I mean the photograph and the paint, is a common one or an original one of the photograph. This paper proposed to use the generative AI to decide if an element is original or not. So the paper basically states that more commonly expressive features appear in the generative AI model's training dataset. I mean, the more generic they are, the more likely the generative AI models are to utilize them when generating new works. So the paper did some experiment to show that this is the case. So for the first experiment, they show that the generative AI model will generate circle with the same distribution as in the training dataset. And for the second one, it shows that the generative AI will try to use some generic element to fill in the blank of an image. So this paper is basically not related to the TDA method, so we'll just introduce this very simply. But it does leave us some insights that can be think about later in the direction of copyright issues in generative AI, and some TDA methods try to resolve it. So first, the memorization of an input content does not really necessarily equivalent with the copyright infringement, because the element memorized by the model might just be a generic or common element, which will not be seen as a copyright infringement on the court. And in result, some safeguard algorithms, such as the data filtering, the differential privacy inspired techniques, and maybe machine learning we mentioned earlier, might limit the model production to outputs that are not over-influenced by any particular copyrighted work within their training dataset. But could TDA methods, so the one directly estimate the influence of particular copyright work helps this? This could actually be a really interesting future work and direction. So thank you for attending this reading group. These are the 4 papers we talk about in this meeting. Okay, thank you.
Thank you.
Okay.